Soundness or deduction means that if we accept some formulas as true and then deduce another formula from them, then also that other formula is true. This is the whole point of logic. More exactly, soundness or natural deduction means that deductions respect truth in the following sense. If a formula A can be derived from the assumptions B1 to Bn, and VB1 equals and so forth equals VBn equals 1 for some valuation V, then also VA equals 1. We now prove this fact. So we prove a theorem. We prove that if V is a valuation, and in addition we assume that A has a natural deduction from formulas B1 to Bn, such that VB1 equals and so forth VBn equals 1, then also VA equals 1. The proof is a kind of proof by induction on the structure of a natural deduction. We proceed from simpler deductions to more complex ones. We show that every deduction is sound in the sense that if in any valuation the assumptions of the deduction have value 1, then so does the conclusion. We proceed from shorter deductions to longer ones. The shortest possible deduction consists of just one formula A, and this formula is both the assumption and the conclusion of the deduction. Of course, such a deduction is sound. Next, we look at deductions in which some rules have been actually used. Every deduction has a unique conclusion and some last rule that has been used to derive that conclusion. All the deductions that have been built before the last rule was applied are shorter. Since we assume that shorter deductions are sound, we may assume that when the last rule is applied, all the previous deductions are sound. So if we assume that the valuation V gives value 1 to the assumptions of a big deduction, the value 1 in a sense flows along the rules until it reaches the conclusion, and then the conclusion also has truth value 1. Let us look at the conjunction introduction rule. So we assume that the last rule in a deduction, perhaps a big deduction, was the conjunction introduction rule. Since we assume the soundness of the shorter deductions, we can assume that we have a valuation V which gives value 1 to A and B. We have to show that the value of the conjunction is 1. But this is trivial. Almost all cases of this proof are trivial, because the inference rules and the definition of the truth value are both based on the same idea. So we have set up the system so that this proof goes through smoothly. Here is a conjunction elimination rule. So we assume that this rule is a last rule in a big deduction. And since we assume that the shorter deductions are sound, we may assume that A conjunction B already has value 1. We have to show that VA and VB are 1. But again, this is entirely trivial. Follows immediately from the definition of the truth value of conjunction. The next rule is disjunction introduction rule. We assume that A has value 1, and we have to show that A disjunction B has value 1. But this is trivial. This is how the truth value of disjunction is defined. The same if we assume that B has value 1. Again, immediately we can conclude that A or B has value 1. So, also the disjunction introduction rule preserves the truth. Disjunction elimination rule is a bit more complicated. So we assume that A or B has value 1. We also assume that the derivation of C from A as well as the derivation of C from B are sound, that is, if VA equals 1, then VC equals 1, and if VB equals 1, then VC equals 1. We have to show that C has truth value 1 in this valuation. But if the disjunction A or B has value 1, then A has value 1 or B has value 1. In either case, we have VC equals 1. Hence, indeed, C has truth value 1. Implication introduction rule. We assume that the derivation of B from A is sound. That is, if VA equals 1, then VB equals 1. Soundness means that this should be the case whatever V is. Now let us prove for the given V that VA implies B is 1. There are two cases, VA equals 0 and the other case VA equals 1. In case 1, VA equals 0 and clearly VA implies B is then 1 by the truth table of implication. In the second case, VA equals 1 by assumption. In this case, VB also equals 1. So VA implies B equals 1. Implication elimination rule. We assume that V gives value 1 to the assumptions, and then by the soundness of the shorter derivations, it follows that VA implies B is 1 and VA equals 1. We need to show that VB equals 1, but this is entirely trivial. Equivalence introduction rule. We leave both the formulation of the claim and the details of the proof as an exercise. Equivalence elimination rule. We leave both the formulation of the claim and the details of the proof as an exercise. Negation introduction rule. We assume that the inference of the contradiction B and not B from A is sound. That is, if V is any valuation and VA is 1, then V, B and not B equals 1. But V, B and not B is 0 always, so it can never be 1. Hence, for the given valuation V, VA must be 0. And then V negation of A is 1, as we wanted. Negation elimination rule. We assume V negation negation A is 1. We have to show VA is 1. This is completely clear. And the proof is ready. We have proved what we wanted. The soundness theorem of propositional logic says that if a propositional formula has natural deduction, then it is a tautology. More generally, if a propositional formula A has a natural deduction from assumptions which have truth value 1 in evaluation V, then also VA equals 1. We have just proved this important basic fact. It is remarkable that also the converse is true. Namely, if a propositional formula is a tautology, then it has a natural deduction. This is called the completeness theorem of propositional logic. Its proof is not very difficult, but we omit it. Applications of soundness. We can show that the formula B is not derivable by natural deduction from a formula A by finding a valuation V such that VA equals 1 and VB equals 0. For example, we can show that the formula P0 or left parenthesis P1 and P2 right parenthesis is not derivable from left parenthesis P0 or P2 right parenthesis implies P1 by letting VP0 equals VP1 equals VP2 equals 0. Then V left parenthesis P0 or P2 right parenthesis implies P1 equals 1, but V P0 or left parenthesis P1 and P2 right parenthesis equals 0. It is important and useful to be able to write derivations, but it is equally important to be able to say why in some cases a derivation is not possible.